Good morning, students. In the last session, we were dealing with moment of inertia and radius of gyration. We already studied moment of inertia means it is the rotational inertia of the body. That means if the body is having more moment of inertia, it is difficult to rotate a body which is at rest. Similarly, if the body is rotating, it is difficult for us to stop. And this moment of inertia depends on many factors. We studied it depends on the mass, it depends upon the distribution of mass, it depends upon the axis, and it depends upon the orientation. So, all those things are the factors that the moment of inertia depends. And we studied for the system of particles, the equation for moment of inertia is I is equal to mr square. That is the expression for the moment of inertia, I is equal to mr square. And for a system of particles, we can say I is equal to mk square. So, for a single particle, I will be doing I is equal to mr square, and if the rigid body consists of system of particles, then I can take I is equal to mk square, or I can take I is equal to sigma mi ri square. Okay. So, here we are going to derive a relation between torque and angular momentum. Torque and angular momentum. We have already studied tau is equal to r cross f. Tau is equal to r cross f, and L, angular momentum L, is equal to r cross p, perpendicular distance into linear momentum. L is equal to r cross p. Now, I am going to differentiate this equation with respect to time. Differentiate this with respect to time. So, what will you get when we differentiate? dl by dt is equal to d by dt of r cross p. These two are separate functions. R is the position vector and p is the linear momentum. Both of them are separate functions. So, we have to differentiate them separately. So, what I am going to do is dl by dt is equal to r cross dp by dt plus dr by dt cross p. So, what I did is, I told here there are two functions r and p. So, when I differentiate it, I am using a rule which is called product rule, and in that product rule what I do is, I take the first function without differentiating, take the first function and differentiate only the second function. So, r cross dp by dt plus differentiate the first function and take the second function without differentiating. Okay. So, I will do like this: first function into derivative of second function plus second function into derivative of the first function. Okay. So, that is how we are differentiating it. Now, we already know dp by dt is equal to f. This is by Newton's second law, dp by dt is equal to F, and dr by dt is equal to V, rate of change of position is called velocity, and P can be written as m into V. So we have these three things. I am going to substitute these three things in the above equation. So I will get dl by dt is equal to r cross, instead of dp by dt, what should I write? F, plus dr by dt is written as V cross, instead of P I will write m into V. So dl by dt is equal to r cross F plus m into V cross V. We already studied any vector crossed by itself is 0. We studied in vector algebra, a cross a equal to 0, b cross b equal to 0, because both vectors will be parallel. So a vector, a cross product of a vector by itself is always 0. So I will be writing like this: since V cross V is equal to 0, and what is R cross F? Torque. R cross F is equal to torque. So I substitute both of them there. So I will be getting the equation dl by dt is equal to R cross F is torque, and V cross V 0. So this term becomes 0, and here I will get torque. So I got the final answer, dl by dt is equal to torque. So this is the relation connecting torque and angular momentum, and this relation tells that torque is rate of change of angular momentum. You think like this: force, rate of change of linear momentum. So force is the rate of change of linear momentum, and torque is the rate of change of angular momentum. That's the difference between both. Okay. So this is analogous to Newton's second law in rotational dynamics. In the linear motion we write F is equal to dp by dt. In rotational motion, Newton's second law is written as tau is equal to dl by dt. So this is the Newton's second law in rotational dynamics. Okay. So please take down the notes. Now we are going to derive one more expression, that is the relation between rotational kinetic energy and moment of inertia. Rotational kinetic energy. So we already know the equation for the translational kinetic energy. When a body is moving in a straight line, the straight line motion is called translational motion. So we already know the equation for translational kinetic energy, that is half mv square. Now we are deriving the equation for rotational kinetic energy in terms of moment of inertia. Consider a rigid body rotating about an axis with uniform angular velocity omega. So I am drawing a rigid body of any particular shape. There is no specified shape, any random shape you can draw, and this is the axis of rotation. Angular velocity I have marked as omega. The meaning of this figure is, imagine like this, this is the axis of rotation, and this is the axis of rotation, this is my rigid body. This rigid body is rotating like this. Okay, rigid body is rotating like this with uniform angular velocity. That is the meaning of this figure. So this rigid body consists of many particles. It's a rigid body of n number of particles. So let us say I am taking many particles like this. This is M1, M2, M3, etc. Mn. There are n number of particles, and distance from those particles to the axis of rotation can be given as this. This is R1, this is R2, R3 and Rn. Many masses are at different positions, so accordingly the distance also will vary. So I already told the rigid body is rotating with uniform angular velocity omega. So omega is constant. So I wrote, consider a rigid body rotating about an axis with uniform angular velocity omega. Rigid body consists of many particles. So I take the velocities of each particle. Okay, so velocity of the first particle V1 is equal to R1 into omega, V2 is equal to R2 into omega, V3 is equal to R3 omega, like that, Vn is equal to Rn omega. So I wrote the velocities of different systems of particles. So linear velocity of each particle is different, whereas the angular velocity, that means omega, angular velocity of all the particles remains same. Therefore, I can write like this: the rotational kinetic energy is equal to half m1 v1 square plus half m2 v2 square plus etc. plus half mn vn square. So I wrote the kinetic energy for the n number of particles. Now we already written v1 is r1 into omega. So what is v1 square? R1 square omega square. So rotational kinetic energy I am writing like this: Ke subscript rotation. So I just wrote ROT, Ke rotation. Rotational kinetic energy half m1 v1 square. V1 is r1 omega. So v1 square is r1 square omega square plus half m2 v2 square is r2 square omega square plus etc. plus half mn. What is Vn square? Rn square omega square. So rotational kinetic energy is half is common. So I'll take half outside, m1 r1 square plus m2 r2 square plus etc. mn rn square into omega square. So what I did is half is common, omega square is common. The remaining thing I put it in the bracket. Now in the last class we studied m1 r1 square plus m2 r2 square etc. mn rn square is moment of inertia, right? So I am writing like this, but m1 r1 square plus m2 r2 square plus etc. plus mn rn square is equal to sigma I is equal to 1 to n mi ri square. This we wrote it in the last session. In the last video we wrote when there are n number of particles, this is the moment of inertia, and this can be written as half I is equal to not half, sigma I is equal to 1 to n mi ri square. So this is actually the expression for the moment of inertia. Therefore instead of this bracketed term I can write moment of inertia, right? Therefore kinetic energy of rotation becomes half I omega square. So you think like this, translational kinetic energy is half mv square and the rotational kinetic energy is half I omega square. So the value of I will change depending upon the axis of rotation, and depending upon the axis of rotation, depending upon the distribution of mass, everything. As I changes, you can say that the rotational kinetic energy also changes. Okay, so that's all for this section. Please take down the notes. Thank you.